Okay, today we're going to explore inverse functions, what they are, how you get them, and how they relate to the initial function that you start with. You should have with you the handout that we gave you in class today, also maybe some colored pencils and your calculator, and feel free to pause the video anytime you need to in order to take the time to get the values that you're going to need or to do the graphing that you need. Okay, first thing we're going to do is fill in the table. Remember that this notation means, the f of x notation, means that if I'm asking you to fill in the -2, you should get -4, and that really what I'm asking you to do is to take -2 and plug it into the function. So you'll have 1/2 of -2 minus 3, and that's how we got the -4. When you're done, this is what you should get. If you need to pause it while you get these values, go ahead and do that, but you should end up with -3.5, -3, -2.5, and -2. Then in step 2, all I want you to do is flip the values in the table so that what was the x value, the -2, is now the y value, and what was the y value is now the x value. So the -4 that was the y value up here is now the x value down here, and vice versa. So go ahead and fill in the rest of the table. And you should end up with that. Okay. Next thing, step 3, I want you to write an equation of a line for step 2. Note that it is linear, and I want you to write the equation of a line, use point slope. You can use any 2 points that you want and write an equation of the line. So pause the video, do that, and then come back and make sure you get the same one that I get. This is what I got, y equals 2x plus 6, and we want to call that g of x because it's a function, it's also a line. Okay, then in step 4, we want to do what you just did in step 2 and 3, but we want to do it for everything, not just these particular x's and y's, not just these guys, but for all x's and y's. So to do that, oops, I'm going to move this. To do that, I'm going to scoot this down and interchange the variables, which means I'm going to interchange all of the x's and y's. So this was y equals 1/2 x minus 3. Now, where I had the y, I'm now going to put in an x, and where I had the x, I'm now going to put in a y. So I end up with x equals 1/2 y minus 3. Now you need to solve that for y, so I'm going to add 3 to both sides, multiply by 2, and I end up with 2x plus 6. And I'm going to call that h of x. So what do you notice about h of x here and our g of x up here? It should be the same thing. And then write a sentence now about why you think that should happen, or why you think that did happen. Once you've done that, I'd like you to come down here and remember what you did with composition of functions. We want to do f of g of x, but we don't want to do it for a particular value for f and g. We want to do f of the entire function g of x. So we said our g of x was 2x plus 6. So I want to plug that into f, the 2x plus 6, and that's going to give me 1/2 of the 2x plus 6 minus 3, which equals 1/2 of 2x is x, 1/2 of 6 is 3, minus 3 equals x. Now go ahead and do the same thing for g of f of x. We want to take g of our initial function, 1/2 x minus 3, and see what you get. You should end up with x. So why do you think that is? Why do you think it happens that if we do f of g of x, we end up with x, and g of f of x, we end up with x? Moving on to the next page. Now I want you to go and do a graph of those two functions. So go ahead and pause the video and do that, including drawing the line y equals x. So I'm going to put in, here's my y equals x line, and I'm going to start for y equals, here's my f of x, is 1/2 x plus or minus 3. And I'm just drawing here, you should be too. I'm going to go up to 6, and then my slope is 2. So I end up with that line. Okay, check to make sure your lines look like this. Write a sentence about what you notice and what you notice about the coordinates for f of x compared to the coordinates of g of x. When you're done, come back to the video. What you should have noticed is that the x and the y coordinates are interchanged. If we look at the point, let me see where the pointer is, here we go. If we look at the point right here, this point, this is 4, -1, that should compare to the point up here, which is -1, 4. And we should see that algebraically, that the x's and the y's got interchanged, but also we should be able to see that graphically, that the point here matches with the point up here. That this point right here pairs with this point right here. And in fact, we have lots of those paired points this way and this way. And if you fold your paper along the line, all of those points should match up. This line y equals x, right here, this line, that is a reflection line for a function and its inverse. So go ahead and fill out the properties of inverses. Sentence down here, you should end up with that m of c of x equals x, and that c of m of x equals x. The idea is that turning x into the x value into the y value, and then the y value back into the x value, because you do the function, then you do its inverse, you should end up with what you started with. And graphically, that means it reflects across the line y equals x. All right, take some time to work through, well, actually, I'll work through number 1 with you, and then we can practice. For this one, you should end up with interchanging the x and y, so now you have 2x plus 8 equals 8 times y plus 3. So now we've interchanged the x's and the y's. What was the x up here became the y here. What was the y here became the x. And now I'm going to solve for y. So I'm going to end up with 1/4 x plus 1 equals y plus 3, and then y equals this, which is this, oops, which is my inverse. And I'm going to call, all right, so that's the y value. So, any questions on that? You should write them down on your sheet if you do have questions. All right, and then verifying graphically, go ahead and graph it. See that your new line here reflects across the line y equals x with your initial line here. And you may want to put that in slope-intercept form in order to graph that more easily. You should end up with y equals 4x plus 8. So go ahead and graph both of those and make sure that they do reflect across the line y equals x. So just put that in dotted and do your other ones in colored pencil so you can tell which is which. Okay, practice again down here with 3 and 4. Pause the video, make sure it works, and then we'll come back. Okay, so this is what you should have. This needs to be, there we go. This is what you should have ended up with. What I'd like to do now is move down a little and make sure that you know how to verify algebraically that these guys really are inverses. You need to check both pieces of this. So if we call this g of x, you need to check that both g of f of x equals x and f of g of x equals x. So to check g of f of x, we take our f of x function, which is the initial one, the x squared plus 3, and we put it into g. So g of f of x is g of x squared minus 3, and then we say that's going to be plus or minus our stuff, x squared minus 3 plus 3, which gives us this, which gives us plus or minus, and remember this is now absolute value, the absolute value of x. So did we come back with what we started with on this one? You can go ahead and verify number 4. It doesn't have the complicated issue that this one does. We need to finish verifying this, and we still are not quite done, because plus or minus x, this thing that we ended up with here, is not what we started with. We were supposed to start with just x. So we need to worry a little bit about domain issues on this. I'll come back to that, but just put a little star next to this one that this is a problem with domain. Number 4 should be okay. We also need to finish verifying this. So not only did I need to check that g of f of x worked, but I also need to check f of g of x. So I'm going to go back and take my f function, which was, the x squared minus 3, and so I need to have f, I want to take f of plus or minus x plus 3, which is plus or minus square root of x plus 3. That whole thing squared minus 3. Here the plus or minus isn't going to matter, and I'm just going to end up with x plus 3 minus 3 equals x. So it is an inverse in this direction. We'll talk about this part, the g of x part up here, later. Okay, moving on. Practice on all of these. When you pause the video, check to be sure that you can find the inverse. You don't need to verify them, but check to make sure you can get them. When you are done, I'll go ahead and write the answers in. Check to be sure that you know that you got the right thing. So I'm just going to write. Okay, when you're done, you should also think about, are these really the things that you expected to get? For example, in number 5, this is a cube root. What would undo a cube root? What's the opposite operation? Cubing. In number 4, this was a fourth power. What would undo that? A fourth root. Oops, and what did I leave out here? I want the fourth root of that. Okay, so check to be sure that they're what you expect them to be. And then again, some of these are going to have domain issues. We'll talk about that next. Once you're sure you understand this, so I want you to do the same thing that you did before, filling in the table down here, and also doing step 2 where we're going to find the inverse. This notation right here, that means the inverse, f negative 1. It doesn't mean f to the negative 1 power, it means the inverse function for f. So I want to walk you through how to do that. You can go ahead and complete the table. You should end up with interchanging the points 5, 0, -3, -4, -3, 0, 5. Okay, but I want to walk you through completing the square on this one. So if you need to review completing the square, go back and look in your textbook. We're starting out with y equals x squared minus 6x plus 5. Now I'm going to interchange the x's and y's. And notice now we have two y's on the right-hand side, so in order to get y all by itself, I can't just move everything over to the left. What I need to do is complete the square so I can take a square root and get the y all by itself. So I'm going to move the 5 over. And then note that what I really need to complete the square over here is a +9, so I'm going to do the +9 here. So now I have x plus 4 equals y minus 3, that quantity squared, which tells me that if I take the square root of both sides, y minus 3 equals the plus or minus square root of x plus 4, and then solving for y, I get 3 plus or minus the square root of x plus 4, which should tie in with the points that you have down here. Although we're going to talk about domain, it's going to be a little bit tricky there. Okay, I'm going to move all this down. When you sketch this, again, we want to put in the line y equals x, and then this is our original function. It crosses at 1 and at 5, and down here the vertex is at 3, -4, and I'm just picking the points from the table. This comes up like this comes up like this. All right, and then you might want to pause this and go ahead and graph your inverse. It should look like this when you're done. We're going to go out 1, 5, and there's a vertex at -4 here. It should look like that. So if I'm talking about my original function, the one in red for f of x, the domain for that is this, and the range is everything from -4 to infinity. Now I want to go do the domain for my inverse function, that's the one in blue. The domain for that is limited. It starts at -4 on the x-axis and goes out to infinity. But I'm going to get back everything, all real numbers. So what happened to the domain and the range for the original function compared to the domain and the range for the inverse function? You should notice that they flipped. The domain of one is the range of the other one. But that's because, again, we're interchanging x's and y's. Domain is all the x's, they become all the y's. Range is all the y's, they become all the x's. All right, so write a sentence down here that makes you remember that, and then let's move on to the next page. Okay, I want to go back and look at this one for a minute. I'm not going to change anything on it, but I want you to notice our original function, the red one, did not pass the horizontal line test. It was not going to give us an inverse that was also a function. But if we limited the domain for that, if we said that our original function was only for x values bigger than 3, then if we only took the piece out here, if we only took this part, then we would only get back this part, and then it would be a function. We wouldn't have a problem. We could also choose x values less than 3 and get this back, in which case we would only get back these. We'll talk more in class about limiting domains, but be aware that that's one way to get a function back. For your work tomorrow in class, though, think about that as a question, but then don't worry about whether or not you're getting a function back. Okay, you probably remember the vertical line test. It's used to determine if something is a function. So if we look at a graph, something like that, if we can draw a vertical line through it, and everywhere we draw the vertical line, it only goes through the function or through the graph once, we know it's a function. So in our original, the one parabola, was that a function? Yes. Was the inverse a function? No. Remember, it looked like this. We did not get a function because if we drew a vertical line, it would go through the graph more than once. A vertical line is all along are all x's. Think about what happens with an inverse. They're all x's, they become all y's. What would we want to do if we wanted to test if something's inverse was going to be a function without actually graphing the inverse? Well, the vertical line, all the x's, is going to become a horizontal line, all the y's. That's the horizontal line test. So if a line goes through the original function, a horizontal line goes through the original function more than once, it might be a function, but the inverse is not going to be a function. And you can see that on our original function. If we go ahead and draw a horizontal line through there, it passes through here and here one more time, so we know that the inverse will not be a function. Without even having to graph it, we know that it will not be a function. That's the horizontal line test. So go down, let's look at these. You should check, is this one a function? Oops. Is this one a function? Yes, but is its inverse going to be, oh actually, we can put a vertical line through there anywhere and it will be fine, but its inverse will not be a function, because if I draw a horizontal line through the original function, it crosses more than once, so the inverse will not be a function. In this case, for B, the original is not a function. If I draw a vertical line through, it passes more than once. But if I look at that and say that we want to talk about its inverse, any horizontal line I draw here, it's only going to pass through once, so yes, the inverse will be a function. I don't even need to graph it. I know that it will be a function. All right, and then what do you guys think about C? This example over here. Is the original a function? No. Or sorry, yes. Sorry, let's erase that. Yes, the original will be a function, but will the inverse be a function? And the answer is no, because a line right through here won't work. Okay, so let's move on to... Okay, so let's do the first one. I like to graph the inverse by looking at a few key points. One of them might be the vertex. Another one might be the places where the graph crosses the x-axis. When I graph the inverse, I'm going to be looking for matching points. The vertex is at -3, -3 now. So when I interchange x and y, it's still at -3, -3. The original function crosses the x-axis a little past -1, which means that the inverse is going to cross the y-axis, because x's turn into y's, a little past -1. The function also has another intercept close to -5. That's an x-intercept, so on the inverse that's going to be a y-intercept, so down at -5. And then I can connect those and get this as my graph. If I go to talk about the domain in my original function, it's -infinity to +infinity. I can put everything in, but I'm only going to get back from -3 forward. If I look at my inverse function, my domain is everything from -3 forward along the x-axis, but my range is -infinity to +infinity. I'm going to get all of these y values back, no matter how high up or how low down I want to go. Eventually I'll get there. For number 2, again, I want to look at a couple of critical points. One of them is the starting point on the original function is -2, 1. That's going to turn into, on the inverse function, when I flip the x's and y's, 1, -2. So I'm going to go to 1, -2 and draw that as my starting point. The y-intercept on my original function is up here on the y-axis between 2 and 3. So with my inverse, I'm going to go between 2 and 3 on the x-axis and continue up like that. And you can see if I put in the line y equals x, that this will make a reflection over that. And again, the domain for the original one, which is everything from -2 forward, becomes the range of my inverse function, and the range of the original function, which is everything from 1 forward, becomes the domain of the inverse function. So you try the next 2, 3, and 4, and then come back and check your answers. Okay, so I hope your graphs look like these. Answer the question about finding the correct inverse. How is that related to that line y equals x? And then finally for number 5, think about how you might graph the inverse if all I gave you were the coordinates. Okay, the last thing I want to do is talk a little bit about going back to the horizontal lines and think about what makes something a function. Sometimes we might need to limit the domain. So I want to look at